First, we're going to define the stochastic processes. Let omega A P be a probability space and T the time space. T is often the non-negative integers or the extended non-negative real numbers. And if T equals the non-negative integers, then the stochastic process is discrete. If T equals with the extended non-negative real numbers, then the stochastic process is called continuous stochastic process. I'm going to define what a stochastic process is. I will use the notation, the star notation for the Descartes product. This is a two-variable function which maps from the Descartes product big omega. This is a literal omega. It maps to big I. Big I is often the real numbers. This two-variable function is called a stochastic process. If and only if for an arbitrary t from big T, this two-variable function satisfies that xt omega, which maps from omega to big I, is a random variable. Following definition is the definition of the Markov chain, and I'm going to use this notation. So let T omega equals xt omega, a stochastic process. And this stochastic process is called the Markov chain. It satisfies two properties. The first property is to satisfy the Markov property, which means the following. I'm going to use this notation to the generated signal algebra. Okay, maybe a little bit luckier if I write here T0. B is a Borel set of I, and it is this position is a Borel set of I, Bi. So T0 is from big T, and let T1 is bigger than T0, and both of them from the big T. So the Markov property says that the probability of each T1 is in big T with the condition an a T0 equals the probability of x T1 with the condition xt0. So in this case that the xt1 is in some Borel set. Okay, I made a mistake. This is in B. So that means in this case that xt1 is equals with something from the big I, but I had to consider the continuous case too. So this definition satisfies both. The following, I want to prove a statement. The statement is let xn be a discrete Markov chain, and mu is the probability distribution of x0. X0 is the initial random variable in our Markov chain. Then this cross distribution and the transition probabilities determines the Markov chain. And the proof of this statement isn't that complicated. We'll just use the Markov property and the definition of the conditional probability. I'm going to iterate this process. What we'll hear is the generated sigma algebra of those random variables in the Markov chain whose index is less than this index. What we have is exactly what we wanted. The following statement, which we're going to prove, is an equality. Like in the previous statement, let xn be a discrete Markov chain. Then the proof will be similar, just we will use an extra addition called the base rule. Right now we are using the definition of the conditional probability. We're going to use the base rule. I just wrote down the left-hand side. If I iterate in the elements of I, then I can use the base rule because the sum of the probabilities of that thing, so xn equals k1, xn plus xn equals k2, and so on, it will be 1. And now I will use the previous equality, the probability of xn equals k, and with the condition x0 equals I0. I0 is I. I don't know why I wrote I0. This is exactly the P, I, K, and the M, because n minus 0 is n. On the other hand, P, the probability of x n plus m equals j, with the condition x n equals k, x0 equals I, is exactly this probability without the condition x0 equals I because of the Markov property. And that probability is exactly the other transition probability, the pkg in the m, and this is what we wanted. There's a corollary, and the corollary is that the n-step matrix is exactly the p in the power n, where p was the one-step transition probability matrix. So we can define a matrix not just in the non-infinity case, but also in every discrete case. That matrix will contain infinity cells, but that's not a problem because our proof is going to work with that matrix of this corollary, just as using the definition of matrix multiplication. We are using induction for n plus m. For when n plus m equals 1, it's true, and the n plus m equals 2 case is from the previous statement, p ij n plus m, the ij element of the matrix or the two-step transition probability is equals this thing, and this is the formula for the matrix multiplication. So you can see that it holds for n equals 2. Write down something. So using induction,